Hello everyone. This is, I guess, a re-recording of lecture 1 for the course TTIC or CMSC 31150 Mathematical Toolkit. As you know, during the lecture, I forgot to record on Zoom, and so for the sake of completeness, let me also make another video for this particular lecture, and hopefully I'll remember to press record in the remaining lectures. Okay. The informal title for the course is Things I Wish I Knew in First Year of Grad School. It's a course intended for first year graduate students. Well, when I was a first year graduate student, I was interested in theoretical computer science, but hopefully this material will be useful for first year CS grad students in general. In terms of logistics, the lectures will be taught via Zoom. The discussion section, office hours, etc., will be held on Gather. The information for all of these is available on Canvas. So all of you should have access to the Canvas page for the course where you can look up all these details. The course also has a Slack workspace. You can use it for discussions on homework problems, questions about the lecture, or just anything else. You can also use Canvas for discussions if you like, and we'll respond to messages on either of these, whichever you prefer. There are two TAs, Shashank Srivastava and Tushant Mittal. They'll also be leading the discussion sections and holding office hours, and feel free to reach out to them if you have any questions during regarding the course. Of course, feel free to reach out to me. Just in terms of timings, etc., lectures will be on Tuesdays and Thursdays. The discussion section for the course will be on Wednesdays, 4 to 5 p.m. on Gather, and Shashank, Tushant, and I will also hold office hours on different days. Hopefully, at least some of these slots will be convenient. You're welcome to come to any of these office hours and discuss any questions that you may have. There is no assigned textbook for this course. I will be posting notes as we go along, written notes, as well as, of course, you can refer to the Jamboards through the Canvas page, where I'll also have the link to each Jamboard used for each of the lectures. The course will be evaluated based on homeworks and midterm and a final. There will be 5 homeworks, totaling 60% of the grade, and then also a midterm and a final. Both the exams will be take-home exams. There'll be a period of 3 to 4 days when you'll be able to start the exam and submit it within some limited period of time, which we'll decide based on the length of the exam then. Hopefully, yeah, we'll try to keep it the period during which you can take the exam flexible enough that it shouldn't conflict with anyone's schedule. In terms of the content, course has roughly 2 modules, linear algebra and probability. Each of these will constitute roughly half of the course, and within each of them we will spend some time kind of covering basics or some foundations in each of these areas, and spend some time on kind of applications of these basic ideas that we will develop for each of them. And then we may also spend some time on topics which are applications of both of these. Such as maybe spectral graph theory or some sort of probabilistic inequalities for random matrices. Or, so there's a list of topics in the course webpage, and then we'll see, depending on how much time we have towards the end of the course, to cover these kind of applications. You may be familiar with some of the basics we will cover, or some of the applications, but hopefully there will be an interesting enough mix to have some new content even if you have seen some of this material before. We will focus on an kind of abstract treatment of both these areas. And I mean, one goal for this course is also to serve as an introduction to maybe a rigorous proof-based style of reasoning. So we will focus on proofs, and in particular, in the homeworks, we will try to sort of emphasize correct and well-written proofs. In the exam, sometimes, yeah, I mean, it's sort of there is time pressure, and so the exams will be aimed at testing the understanding of certain concepts. But for the homework, especially, we will look for correctly written proofs. Also, the abstract treatment of some of the things in terms of linear algebra, for example, instead of talking of matrices, we'll be talking of operators. Instead of talking about dot products, we will refer to very generic inner products. And so we will try to take an abstract view of some of the concepts that maybe you may have seen in a different form earlier. Some of these ideas, it's also one of the things we want to emphasize in the course is that maybe some of these things, relatively simple kind of concepts which we all have probably seen, but viewed in an abstract way, they are surprisingly general. They have a very they have a surprising expressive power, and they lead to a huge number of applications, and then we'll see some examples throughout the course. Okay, and of course, yeah. So I'll try to keep the lectures interactive. I'll try to give examples during the lectures, but please feel free to interrupt me at any point. Feel free to ask questions. Unfortunately, this is a re-recording and there's no opportunity for asking questions, but I'll try to remember and mention the comments that came up in the class when we discussed this. Okay. Today we'll kind of just probably discuss some relatively basic definitions of fields and vector spaces from linear algebra. If you're familiar with some of this stuff, I usually like to give out some puzzles which can be solved just using linear algebra, but maybe on the face of it, they don't seem like they're about linear algebra, and you can try to think about these. Both of these are taken from the excellent book by Jiří Matušek called 33 Miniatures. It's also linked from the course webpage in the resources section. And okay, the first one is just, let's say you have a rectangle. So sides are say 1 or root 2. Root 2 can be replaced by any irrational number if you want. Question is, can you tile it with a finite number of squares? The sides of the squares can be rational, irrational, whatever. We just want squares which are non-overlapping and they cover the entire rectangle, and there's finitely many of them. And the goal is to prove that this cannot be done. Try to think about it. And another one is also some sort of a covering problem. So let's say we have the complete graph on n vertices, and we want to cover now all the edges of this graph by kind of bipartite graphs which go between a set S and a set T. Let's say S and T are disjoint. So every pair with one vertex from S, one vertex from T contributes an edge. And let's say you have m such graphs with m such kind of complete bipartite graphs, such that every edge of our complete graph on n vertices appears in exactly one of them. And the goal is to show that you need at least n minus 1 graphs to do this. And again, you can find the solutions in the book I mentioned. but I still encourage you to think about these problems, and you can find many other interesting problems if you like that sort of thing. It's a beautiful book to read and quite fun. Yeah. All right, so now let's start with the concepts we want to discuss. The first, the concept of fields, and basically before we do any sort of algebra, we want to just do arithmetic, and fields are basically sets of objects over which we can do arithmetic. So just usual operations, maybe addition, multiplication, division, whatever you're used to in arithmetic, but abstractly, what is a set over which you can do this stuff? And the definition of a field is just given by defining two operations, an addition operation which takes two field elements and sort of takes two objects and adds them to give a new object, which is again from field. And we are used to doing this over all kinds of numbers, but just more abstractly, we'll define this operation mapping two field elements to a field element. Same with this kind of dot or multiplication operation, which maps a pair of field elements to field elements. And we'll require these operations to satisfy a few properties. Again, these are properties which we are familiar with from various kinds of number systems, from real numbers, complex numbers, rational numbers. But the point is that we want to just sort of define a field abstractly in terms of these properties rather than specifically in terms of any number system. Just as long as we can do all these operations, we'll call this set of objects a field. Okay. And commutativity is just that you can add two objects and it doesn't matter which is the first one, which is the second one. Same for multiplication. And associativity is sort of similar, that you want to, let's say, add three objects. So because our operations are only defined on two at a time, you will have to pick which two you add first, and then you take the result, add it to the third one. So sort of the order in which you put brackets. And again, associativity says it doesn't matter where you put the brackets or how you kind of reduce this problem of adding three things to adding two things. They will all give you the same answer. Same for multiplication, again within the field. So you can put brackets in any order. Identity element, so this we need both for addition and multiplication. This identity is again the analog of the number 0 and the number 1 in number systems. And in general, this is just an kind of object in this field. And the identity element is just something. So there is some object in the field, which, well, we now just say the analog of the 0 number, but now in this field, such that when you add it to anything, you get the same thing back. Okay. So this is what happens for the number 0. And again, we are just saying that there should be at least some field element which satisfies this with respect to sort of howsoever we chose to define this addition operation inside this field. Okay. And similarly for multiplication, we will say that there exists some element in the field such that when you multiply it with anything, you get the same thing back. Okay, and the definition of inverse is kind of trying to capture that we define addition and multiplication, but not subtraction and division. And these are just operations that we get by some sort of, we think of subtraction as the inverse of addition, division as the inverse of multiplication. And so formally speaking, we define these as saying for every element or object in the field, there exists another element, A prime, such that the two together add up to whatever was this number which acted as a zero element or the identity for addition. And this is kind of nice because we will think of when we want to sort of subtract A, we will just add this A prime. So we will think of this A prime as minus A. Okay. So subtraction we will basically just define using additive inverses. Okay. We will not specially write down a subtraction operation. Similarly, we will sort of define this kind of division operation and or by saying that there is a multiplicative inverse. So for every A, now we will say that it should not be the zero element because again, division by zero doesn't even work over the number systems, or the rational numbers, even it doesn't work. And so for every non-zero element, we will say that there exists an A prime such that when you multiply them, you get whatever is the multiplicative identity of the field. And again, this we will think of as the kind of 1 over A, or the division by. Okay. And finally, distributivity is this is a kind of slightly different property because it combines both addition and multiplication as opposed to all the previous properties. And sometimes it says if you kind of first do addition and then multiplication, you can kind of open up the bracket. So you can first do the multiplication appropriately, I mean, in sort of for both A times B and A times C, and then add them up, and you will get the same result. Okay. So these are just some properties which we are kind of used to from our notions of numbers, but here we are trying to capture in an abstract way that as long as sort of you have any set of objects and any operations which satisfy these properties, we can use it to do arithmetic. And it's sometimes interesting and useful to do this for objects which are a bit different from, let's say, real numbers, rational numbers, or complex numbers, stuff we are familiar with, but may still have ways of defining addition and multiplication over time. Okay. So let's continue and see some examples. So the first example is okay, actually, before we go to examples, let's also develop a useful consequence of these properties, which comes in quite handy. So it's a property that if you have A and B, which are such that their product or the multiplication is zero, then we know, or we can say using these properties, that either A is zero or B is zero. So in particular, if A is not the zero element, then well, it has an inverse. So so we can write A inverse times A times B is equal to A inverse times 0. So just multiply on both sides by the 0 element. And now, because of associativity, we can compute this first, and we get B is equal to A inverse times the 0 element. And you can also check that anything times the 0 element will be 0. So you end up getting that B is equal to 0. So if A is not equal to 0, then B must be 0, and that's a consequence of just the properties we define. Okay, so now let's go to some examples. So the examples where we are already familiar with notions of addition, multiplication, subtraction, and division, rational numbers, real numbers, complex numbers. Importantly, note that in integers we have addition and multiplication, but if you divide two integers, even if the denominator is non-zero, you will not end up necessarily with an integer. So it's not an operation which maps pairs of integers to integers, and that's a problem. And so we don't always have inverses in that sense. And so we have to at least start with rational numbers if we want to work with this kind of addition and multiplication. But yeah, all of these define valid notions of addition and multiplication. Okay. Here's another attempt to try and define a notion of addition and multiplication, but this time for pairs of rational numbers instead of individual rational numbers. So here's how I propose to add these and kind of multiply these. And let's say I think of a pair as A comma B, and then I'll just add them coordinate wise. So A comma B plus C comma D is equal to A plus C and B comma D. Sorry, B plus D. Similarly, for multiplication, I will say sort of the first coordinate. So the result also has to be a pair of rational numbers. So I will say the first rational number is A times C and B times D. So and the second is kind of formed by looking at A times D and B times C. And this is some notion. It takes two pairs of rational numbers and gives me a pair of rational numbers. So it kind of at least has the right type. The question is, does it satisfy all the kind of properties that we wanted? And here, I guess this was asked in the class, and people did point out that it doesn't. But let's start with a more basic question that does addition work? And turns out addition does work because you're kind of doing the same thing that you were doing in terms of adding rational numbers. It's just that you're just doing everything twice. So, and yeah, this is an abuse of notation that will happen throughout the course, but note that the plus symbols on both sides are a bit different. So here, this plus is something I'm trying to define. And this plus is something that is already defined. So this is something I'm trying to define over this new space that we are talking about. And this is the known operation over rational numbers that you already know of, but it's kind of clear from the way things are written that what are the objects we are trying to add. But we will possibly work with different notions of addition and multiplication in the same statement, and we will not always write them or distinguish them by notation. It will just be too cumbersome to do that for every single thing we write. And this is something which we may need to get used to and sort of remember. Similarly, here, this notion of product is something I'm trying to define, whereas there is kind of an implicit product here of two rational numbers. And there is a summation here again of rational numbers, and these are all known and defined over rational numbers. Okay. Now, going back to the additive part, I claim the addition still works, and in particular, you can think of the additive identity as 0, 0, which still works as the additive identity over this. So, and you can check that if you kind of have add 0 in each coordinate to a pair of rational numbers, then neither of the coordinates changes. So this is a valid additive identity, and now we can kind of violate the property that we talked about earlier, that if you have two non-zero things, you multiply them and you get 0, and this shouldn't happen. So in particular, you can check that if you multiply according to the above notion, 1, 1 and 1 minus 1, you end up getting 0, 0, which is problematic, because we said whenever you have a product of two things being equal to 0, this can only happen if both of them were 0. Okay, so that's maybe an example of an attempt which doesn't work. I claim that you can change this a little bit and then things do work. So instead of defining it as AD plus BC, suppose I kind of defined it with a plus here and a minus here. Then this example is no longer a problem. And actually, let me just leave both definitions there. So originally we defined it with plus, for which we had a counter example, but we can actually change that and replace it by a minus. And this does work. And you can think about it, it's actually as if you were thinking of a comma b as the real and imaginary part of a complex number and just multiplying the corresponding complex numbers. So this can just be derived from the usual addition and multiplication over complex numbers, which satisfies all the properties because the set of complex numbers is a field. And this is just a way of writing it in which it may not be entirely obvious. There are also interesting variations of this that you will see in the homework, but in particular, if I change this to AD plus 2 times BC, it still works, and this is still a valid notion of multiplication of pairs of rational numbers. And now maybe not kind of entirely natural one, but again, you'll see that it's a very a valid one, and again, it can be derived in a sort of relatively easy way. Okay, so these are just some examples to maybe keep in mind. Another very important example that comes up a lot in applications, or comes up a lot in various sort of objects or settings that we might be interested in, is the so-called finite field. It's a field of finite size. In fact, we will only be interested in fields of, let's say, prime size for now. So this is just a list of numbers 0, 1 to p minus 1, where p is a prime number. And we will define addition and multiplication over this. So again, this is a new notion that we are trying to define, and we will define it in terms of an existing notion, which is just if you had two natural numbers, how you would add them. So this is just a multiplication or addition over natural numbers, which is well defined, let's say. But then importantly, we consider the result modulo p, or we just divide by p and take the remainder. Same for the product. Okay. So over natural numbers, I said addition and multiplication doesn't necessarily have an inverse, and that's why natural numbers themselves are not a field. But if we do the addition and multiplication over natural numbers, but at the end of the day, also take this remainder modulo p, and if p is a prime, then it turns out that we do have kind of multiplicative inverses and all the good stuff that we want. And it satisfies all the properties of a field. And in fact, these are very useful fields, and then we'll see them fairly often. They arise in many settings, such as cryptography or analysis of algorithms, particularly randomized algorithms. And sometimes you'll also find them as being referred to as GFP, or the Galois field of size p. I mean, I should say that to define fields, we don't necessarily need p as a prime number. It can also be, turns out, a power of a prime number to define finite fields. Although, yeah, we'll restrict ourselves to prime fields just because they are slightly easier to describe. And just as a sanity check, an exercise, and again, I'll keep assigning exercises throughout the course as we go along. I recommend trying them out regularly after the lectures, and also please feel free to come and discuss them during office hours or during the discussion section, or ask me in a later lecture if some exercise from the previous lecture has been really bothering you and you want to discuss it. But it might be, yeah, I mean, especially if some of these concepts, if one of them is new for you, then make sure you try out at least some of the exercises just to sort of practice a little bit in terms of how to apply the definitions, etc. All right, so a couple of exercises. You can check that if p is not a prime, and especially just as a simple example, just try to think of defining operations modulo 6. So instead of 0 to p minus 1, let's think of the numbers 0 to 5 and define their addition and multiplication modulo 6 now. And then I claim that it sort of the properties that we want for the field are not satisfied anymore, and one of the properties at least fails. And think about which one. Another one, which is an example to try, is that, okay, again, this sort of strange set of real numbers, which are of the form a plus b times cube root of 2 and c times cube root of 4, where a, b, c are rational numbers, is this set is a field. And yeah, when I say something is a field, it means that you have to define some notion of addition and multiplication over these elements, etc., to and then prove that this notions of addition and multiplication satisfy all the properties we talked about. So yeah, you can think about how you may want to define all these operations. I mean, yeah, okay, you can think about it, but otherwise feel free to discuss it in one of the sections. All right, now let's go to the next concept I want to discuss, which is maybe a slightly more generic setting. And these are kind of sets of objects we call vectors, and these the sets themselves are referred to as vector spaces. Some sense, the definition of a field is a bit restrictive. It's kind of very nice that we can do arithmetic operations over them that we can kind of add and multiply. But turns out that if we really insist on a setting where we can kind of add any two things, multiply any two things, define division and so on, then we can't quite describe everything we want. And for example, yeah, I mean, if you have vectors with sort of real coordinates or lists of numbers, it's not always clear what it means to kind of what are good notions of addition or sorry, not addition, what are good notions of multiplication and division, which kind of gives you objects of the same type. And one can define some, but I mean, it's possible that the application we have in mind needs a different way of treating these objects. And so a slightly kind of larger class of spaces where we require fewer properties. So in some sense, yeah, so these are things which are built on top of a field. So you have an underlying field where you can do all kinds of arithmetic operations. And then on top of that, we will look at a set of objects which we will call vectors. And we'll still require that for any two vectors, you want to be able to add them together. And so if this will have all the usual properties in terms of kind of inverses and commutativity, associativity, etc. But we'll kind of give up on multiplying vectors. So we'll not say that we need to multiply any two vectors. What we want to be able to do is to sort of scale them or multiply them by a field element. Okay. And so this is sort of a mixed operation now. This dot has a different meaning than what we talked about before. And we will also refer to field elements as scalars as opposed to, well, vectors. Okay. And properties we want are not very different from the kind of properties we discussed earlier, at least formally, although the type of objects that participate in them may be different now. So commutativity is still the same. Notice that I'm only writing it for addition because the kind of things that participate in multiplication are different. The first argument is a field element and the second argument is a vector, and I can't flip their order. I mean, these are, I can't change the types of the two things. Again, for associativity, the property is similar to what we had before. Multiplication, now sort of similar to associativity, but okay, let's write it and then maybe reflect on it for a minute. So and now let's try to put brackets and define this property. So okay, but there is a slight subtlety now that the meanings of these different dots is different, and they are kind of operations of different types. So in particular, when I multiply b with v or a with b times v or a times b with v, I'm multiplying a scalar with a vector. And when I kind of multiply a and b together, I'm multiplying two scalars. So although it's kind of syntactically just looks like different brackets, I'm actually not just kind of multiplying in different order, I'm also doing different kinds of multiplications on the two sides. On the right hand side, I'm doing a scalar and vector multiplication. And on the left, I'm doing one scalar vector multiplication and one multiplication inside the field. So where the two arguments are both scalars. Okay. So that's why it's I mean, yeah, formally kind of looks very much like associativity, but it's just, I want to highlight a little bit that these are two different kinds of multiplications happening. Identity elements are sort of similar, that there exists a zero element in the vector space now, which still has the property that for all elements of the vector space, adding the zero element leaves it unchanged. And identity in terms of multiplication will still be from the field. So I will say that whatever was the identity element in the field for multiplication is such that when I multiply it with the vector, I still get the same vector. Okay. Inverse, again, I'll require for addition. So I'll say that for all u, there exists u prime, such that u plus u prime is equal to whatever was the identity for addition. And distributivity, again, it's we need to be slightly careful about the kind of objects we are dealing with in each of these operations, but sorry. So the multiplication in all of these is a scalar vector multiplication, but the addition on the right is an addition in the vector space, whereas on the left is an addition of scalars or inside the field. Okay. And there can be another kind of distributivity, which is again saying that maybe a times u plus v is equal to a times u plus a times v. Here, yeah, sort of there's not too much to worry about operations. All multiplications are scalar vector and all additions are two vectors. So here there is perhaps less to worry about. Okay, but yeah, we will still use symbols of plus and dot for all these operations without always explicitly specifying which space they are happening in. But yeah, usually it's easy to tell from context. Okay, so now let's go to some sort of more interesting examples of objects where we can construct vector spaces. So first, note that so vector space, I mean, so any field is already a vector space over itself. So for a vector space, we have to specify what is the set of objects, what is the set of vectors, and what is the field over which we are talking about. And may not necessarily be itself, but if it is, then it's always a vector space. And in fact, for any field, if you look at d tuples from that field, then this is a vector space over that field. Maybe slightly different example is if you look at the set of reals, then this is a vector space over the set of rationals. So you can multiply, you can add two real numbers and you can multiply a real number by a rational number and still get a real number. I mean, set of reals is also a vector space over the set of real numbers, but I want to kind of think of it as a vector space over rational numbers. This will have slightly more interesting properties in terms of some objects we'll see, like basis, etc. Okay. Another example is, which is also something we'll encounter a lot, and just to introduce this notation also, which is the set of polynomials, which are nothing but, let's say the polynomials in one variable are just formal sums of the form of coefficients times the power of x. And a polynomial can be defined by sort of powers of x from 0 to any finite number, let's say a finite index t. And when I say r square bracket x, I'm just referring to the fact that the variable I'll be using is x, and this r refers to the coefficients that will appear. In this case, the coefficients will be real numbers. Okay. Of course, you can think of polynomials over other spaces, other fields in particular, and we'll see more examples as we go along. It's again, we know how to add two polynomials. We know how to okay, so here I should have specified what is the field I'm talking about. And for example, real coefficients, and let's say over the field of real numbers. Okay. So I know how to multiply a polynomial by a real number. I know how to add two polynomials, and you can check that they satisfy all the kinds of nice properties that we want. Another piece of notation that we will use is r less than equal to d, which is just used to indicate polynomials where the degree or the exponent of the highest monomial or the highest power of x that ever appears is d. Okay, so I will only consider formal sums which go up to x to the power t for t less than equal to d. And another kind of example of a vector space, also an opportunity to introduce a piece of notation, is, let's say, the space of continuous functions. So in general, I'll use c, x, y to denote the space of functions f from the space x to y, which are continuous. And again, the continuity we'll need to define what is the notion of 2 points in the domain of f being close to each other, 2 points in the domain of y, in the range of f being close to each other. So to define continuity, I'll need to say what are the notions of distances in x and y, etc. But yeah, for real numbers, for the interval 0 to 1, what we know what it means for two real numbers to be close, what is the distance between two real numbers, etc. But in general, this notation is used to define a set of continuous functions. Okay. And then we'll see many more examples of this type. You can check that the sum of two continuous functions is a continuous function, so addition is well defined. And here, by the way, when I say sum, we'll think of adding functions or pointwise. So when I say f1 plus f2 is a function, what it means is that when you want to compute the value of this function at an input x, you look at the value of f1 at x and you look at f2 at x and add them up. And this defines a new function. This defines a function which still takes the same kind of inputs and gives the outputs as real numbers. And similarly, for when I want to multiply a function by a constant, I will call this thing a new function, such that if you want to compute the value of it, you kind of compute the value of the old function at x and then just multiply it by this number c. And you can check that this also defines a valid notion of addition and kind of multiplication by a scalar, and then gives a vector space. Okay. All right. Another example of a vector space, which is taken from lecture notes on linear algebra and combinatorics by Lazzi-Babai, is a so-called Fibonacci space. You can think of it as a space of functions from, by the way, I mean, Lazzi's course is also linked from the course webpage in the resources section. It's also an excellent resource for finding many practice problems and so on. So yeah, I definitely recommend checking it out. The Fibonacci space you can think of as a space of functions from natural numbers to real numbers, or equivalently a set of infinite sequences of real numbers, such that we always have this property that the value of this function at n is the sum of the values at n minus 1 and n minus 2, as long as all these are well-defined natural numbers, so n is greater than equal to 2. Equivalently, yeah, if you look at kind of the nth element in the sequence, it should be the sum of the previous two elements. So the well-known Fibonacci space or Fibonacci sequence that we know, starting with 0, 1, 1, 2, 3, 5, etc., is a sequence which satisfies these kind of properties. But more generally, just any sequence where sort of every element is the sum of the previous two, as long as there are at least two things before it. I'll just call this collection of all such sequences the Fibonacci space, and you can check that it's a vector space. You can again think about what are the kind of right ways of adding two functions or multiplying a function by a real number, etc. Okay. A concept that we'll use fairly often in vector spaces is linear dependence, and in some sense this is trying to capture, are there kind of any sort of redundancies between the objects we are talking about a collection of objects that we have. And we say that a set of vectors is linearly dependent. So a set S of vectors is linearly dependent if you can pick for some n, you can pick n of them and multiply them with some sort of coefficients that you want. So any coefficients from the field, and end up with the zero element in the vector space. By the way, this sort of expression, which is the sum over vectors which are multiplied by coefficients, is also referred to as a linear combination. So you'll say a set of vectors is linearly dependent if there exists a linear combination of finitely many vectors from the set, which is zero. And it's not like zero for maybe a stupid reason that I just took all coefficients to be zero. 0 times a vector, I got 0, and so I just sort of added 0 a bunch of times. But something more interesting. So not all the coefficients are 0. And if I still end up with the 0 vector in the vector space, then something interesting is happening, and that's when I say that this set is linearly dependent. Note that importantly, I'm only defining a sum of finitely many vectors, and not necessarily talking about any kind of infinite sums. That's because, I mean, formally speaking, an infinite sum is actually a limit of finite sums. And to define the notion of limit, we kind of need to say what is the notion of convergence. What does it mean to say that things which are kind of coming out of these sort of larger and larger finite sums are getting closer and closer together. But so far, we don't have any notions of what it means for things to be close to each other in this vector space. And such notions might not always even exist. For example, if you think of finite fields, etc. So it may not be always possible to define any kind of infinite sums properly, and we will only restrict talking about finite linear combinations, especially in abstract vector spaces. And when we'll get to cases we can define distances, we'll talk more about infinite sums. But for now, it's always finite, finitely many elements in a linear combination. If a set S is not linearly independent, we'll call it, sorry, if it's not linearly dependent, we'll call it linearly independent. Okay. Right. And just to sort of maybe connect to this notion that I was talking about, that this captures when we have some redundancies, I claim that if I have a linear combination, then and I will call it a non-trivial linear combination if not all coefficients are 0. So if I have a non-trivial linear combination which is equal to 0, then there exists at least some vector in this linear combination which I can write as a linear combination of the other vectors. So possibly with different coefficients. I mean, all we are doing is this kind of, I said at least one of the coefficients is non-zero. So pick the vector whose coefficient is non-zero and just kind of multiply by the inverse of that coefficient. And then we move things to the other side. So in this sense, there is some redundancy that I didn't really need, strictly speaking, this vector vi, because the other vectors give me some information about it. Okay. I mean, of course, depends on what we are trying to do with this vector. Maybe it still helps to know this, but it's just redundant in this very specific sense of linear combinations. Okay. As an example, yeah, I mean, I asked in the class if you could give me examples of linearly dependent vectors, 3 linearly dependent vectors in R2. And actually, yeah, the examples people gave were interesting because they illustrated, like, we got 3 examples and they all illustrated 3 interesting different concepts. So first of all, when I say R2, I'm actually talking of the over the field R, just to clarify. And one of the examples we got was 0, 1, 1, 0, and 1, 1, because they satisfy this property that I just said, that one of them can be written as a linear combination of the other vectors. So you can move this 1, 1 to the other side, or multiply, or sort of write the sort of inverse of it, the additive inverse, and then this will be a non-trivial linear combination, which will be 0. The second example we got was kind of 3 vectors which are at 120 degrees and of equal length. And this is sort of another interesting example where we get this linear combination, but for some sort of a geometric reason, and then we'll get back to these kind of examples more often. But it's as opposed to this kind of algebraic intuition that these 2 things add up to the third thing, this is coming from a slightly more geometric intuition. And the third example was also interesting. Sort of the third example was any 3 vectors, which is true that in R2 any 3 vectors will be linearly dependent, and it's also kind of shows that maybe there is some sort of limit to how much linear independence you can have, and yeah, as we will see, depending on what vector space we are talking about, in particular for what are called finite dimensional vector spaces, there will always be some sort of limit to how much linear independence we can have, and this will be something which is inherent property, which is an inherent property of the vector space, and then we'll talk much more about this as we go along. Okay. Okay. Now let's get to another interesting example, which we'll discuss in some more detail. But now let's think of the space of polynomials. Or let's say we have a1 to an, which are distinct real numbers. And let's think of g of x, which is a polynomial which is just product of all factors of the form x minus aj. Notice that this is a polynomial in X, you can kind of expand out all the factors or sort of multiply and write down the formal sum in terms of powers of X. And in particular, the highest power that you will get will be n. So it's a polynomial of degree n, and it's an element of this vector space of polynomials of degree n. More importantly, we can look at polynomials which are of the form, which I'll sort of call fi of x, where I've looked at looking at all the factors except for the ith one. Okay. So formally, I can write it as g of x divided by x minus ai, just in terms of cancellation of factors, or just as a formal function. I mean, yeah, if you want to think of it really as a function where x is a real number, then you will have to kind of extended continuity at the point x when it's equal to ai. But yeah, maybe just think of this definition where I'm multiplying all the factors except the ith one. And this is an element in the space of polynomials of degree at most n minus 1, because there are n minus 1 terms in the product, and the highest power of x that I will get is n minus 1. And I can construct n such polynomials when I ranges from 1 to n. The claim is that these are all, they form a linearly independent set. Again, I'm thinking of the vector space over real numbers as we defined earlier for the space of polynomials. And I want to claim that they are linearly independent in this vector space. Okay. For a proof, and this is sort of what we'll do often when we want to prove linear independence, that suppose we have a linear combination which does give us 0. So we have a linear combination, and the 0 element of the vector space you can check will be the 0 polynomial, which is just 0 plus 0 times x plus 0 times x square if you want. It's just a polynomial which you add to any polynomial, and it doesn't change. So the polynomial to which you are adding it. So and suppose we have such a linear combination, and then we would show that the only way this can happen is if C1 is 0 and C2 is 0 and C3 is 0, so all the coefficients are 0. So there is in particular no non-trivial linear combination which vanishes, and so you have linear independence. The only linear combination which gives you 0 is the trivial one, with all the coefficients of 0. Okay. And the way to check this is just we look at these polynomials and plug in one of the inputs, so sort of plug in one of the values a1 to an. So let's start maybe saying that if these are this linear combination indeed is equal to the 0 polynomial, let's just plug in the value a1 on both sides. So then we get c1 times f1 of a1 plus c2 times f2 of a1. Similarly, cn times fn of a1 is equal to 0. Now this is the number 0, because the 0 polynomial, when we substitute x equals a1, we get the real number 0. Now this equation is kind of actually simplifies quite a bit, because f2 involves x minus a1 as a factor. In fact, everything except f1 involves x minus a1 as a factor. And when you substitute x equals a1, this will be 0. So this will be the 0 real number. And so all of these will be 0. The only thing that will survive and will be definitely non-zero is f1. And this is where we are using the distinctness that these are distinct real numbers. So f1 will certainly be non-zero. But then, because the set of real numbers is a field, the only way this happens is if C1 is equal to 0. So we get that this implies C1 is equal to 0. There was nothing special about C1. We could have plugged in A2 and obtained that C2 is equal to 0 and so on. So similarly, you can kind of prove and so the only linear combination which accomplishes that C1 F1 plus C2 F2 and so on is equal to the 0 polynomial is the trivial linear combination. And that means this set is linearly independent. Okay. Another example, which I'll leave as an exercise to try, is that if you think of the set of three real numbers, 1, √2 and √3, and if we think of real numbers as a vector space over rationals, then this set is a linearly independent subset of the real numbers. Okay. Of course, probably very easy to see that its set is linearly dependent over real numbers. Of course, you can multiply 1 by √2 and √2 by -1 and add them together, and you'll get the 0 real number. But if you're only allowed to use coefficients which are rational numbers, then you can't obtain 0. Okay. Kind of carrying forward this sort of idea of redundancy and what we can generate using linear combinations, etc. The way to formalize this is the concept of span. So again, for a set S, which is a collection of vectors or a subset of the vector space, we will define its span to be the set of all vectors we can obtain by linear combinations of finitely many vectors from S. So, few things to notice. You're allowed linear combination of any finite number of vectors. For the same reasons as before, we're not working with infinite ones, in infinite combinations right now. C1 and C2, C1 to Cn can be any field elements, not necessarily saying that one of them is non-zero. So in particular, the trivial linear combination is allowed, which will give you 0. So 0 is an element of the span. Whatever we can obtain this way, and this is sort of saying that whatever kind of information can be generated by these vectors v1 to vn, we will think of as the span of the of whatever can be generated by vectors from S, we'll think of as span of S. Okay. A special kind of set of vectors which is in some sense has enough information to generate the entire vector space. So the span of this set B is the entire vector space, but at the same time, B has no redundancies in itself, that B is a linearly independent set. And I'll use this kind of Li and Lb, as I've already been using a few times. I'll use them throughout the course just because I don't want to keep writing independent and dependent on Jamboards while I'm lecturing. But a set B, which kind of has this property that its span is everything, but at the same time it's linearly independent, is called a basis. And again, we'll see some nice properties of bases and these kind of sets for various vector spaces. But a nice characterization of basis another useful way of thinking about them, which will come in handy, is to say that a basis is nothing but a maximal linearly independent set. And by maximal, I just means that it is linearly independent, but barely so, that a basis is a linearly independent set. And if I add any vector which is not already in the basis, then the new set is linearly dependent. So if I add anything to it, it's no longer linearly independent. notice that, I mean, I can even add the element 0. This element 0 itself is a single, even just the set 0 is a linearly dependent set, because you can have a non-trivial linear combination 1 times the vector 0, which gives me the vector 0. Okay, so but for the basis, anything that I add to it will give me a linearly dependent set. Okay. Anything which is not already present. And okay, so this is actually an if and only if characterization. We can prove both directions of it. And here I'll only prove one and maybe leave the other as an exercise. So suppose we want to, okay, so first notice that we want to show if B is a maximal linearly independent set, then it's a basis. Basis requires two things: linear independence, and the span of the basis should be everything in the vector space. We're already halfway there, because we know B is a maximal linearly independent set, but in particular, it's a linearly independent set. So all we need to show is that this is what we need to show. And so we can kind of think of two kinds of vectors. So if you have a vector v which is already in B, then this vector is in particular in the span of B, because it's one of the elements. So you can just take that element, multiply it by the scalar 1, and you get the same vector. So and what we want to show is that every vector is in the span of B, but for things which are already in B, this is kind of easy. So we need to mostly focus on vectors which are not already in B. Okay, so so this is a vector in our vector space, but not in B. We want to show that this is in the span of B. Okay, we need to show. Now here we kind of go back to our characterization also of this property of linear dependence that we had. So since this vector is not already in B, we know what happens when we add it to the set B. Because B is a maximal linearly independent set, when we add something, it becomes linearly dependent. So in particular, when we add it, this is a linearly dependent set. What does it mean that this is a linearly dependent set? Well, it means that there exist some vectors v1 to vn, which are in this set, and sort of coefficients c1 to cn, which are in our field and not all 0, such that this is the 0 vector. Now, I claim that one of these vectors v1 to vn must be the new thing that we added, the vector v. If not, we have a linear combination of things which were already there in the basis equal to 0, which can't happen. The basis was linearly independent. So this should have been caused by the new thing that we added. So at least one of these vectors v1 to vn must be v with a non-zero coefficient, because otherwise again, I mean, if it's zero coefficient, it's as if it was not there, right? It's just that you are adding the other things with non-zero coefficients. So and let's say Vn was equal to V. So then we have some linear combination of the others plus Cn times V is equal to 0. And now we can use the additive inverse and say that let's sort of take the additive inverse of all the others. So is equal to Cn times V. And then let's also multiply, because the coefficient of V was non-zero, let's multiply by the coefficient and notice that I'm using properties like distributivity, etc., all over the place. But I can multiply by the inverse of Cn, since it was a non-zero element of the field. And this product is the identity element on the field. And so in particular, I have V here. And I've expressed V as a linear combination of the other field elements. So this vector V that was, okay, yeah, I should have said that I was kind of also maybe implicitly assuming that the vector V was non-zero, because if it was 0, then, well, I mean, it's still true that I can have all the other coefficients as 0 and 1 times the vector V, and the proof would still work. But yeah, 0 is always in the span. It's kind of easy to see anyway, because, well, we can always take the trivial linear combination of the basis elements. Okay, but anyway, this vector V, which was not already in the basis, we showed is in the span of the basis. And so, and things which are already in the basis are easily in the span, because, well, we can just pick the basis element. So everything is in the span, and this is sufficient to show that B is indeed a basis. Okay, let's stop here for this time, and I'll continue from here, and we'll study these basis and vector spaces in a little more detail next time.